care, but
I don't care.
Wayne didn't want to zoom too much. Now he just doesn't carry anymore either, but
Hey, Dominic, what's up?
So for that firewall,
Yeah.
I'm just gonna, because I was looking over the rule book and I couldn't like understand it. I was talking to Myra help. And I guess I have two options with so it's either tape or foil.
Okay.
So I'm just gonna use foil.
Okay.
And I shouldn't have to do any analysis on it.
Okay.
But then for my project, I want to do the head restraint. So
Okay.
it's like the headrest.
Sure.
And then in the rule book, it has to have like withstand a been up too long. A force of 900 newtons,
Okay.
like going directly into it, and then 300 newtons down.
Okay.
So would that be like fine to do?
Yeah. Yeah. I mean, it's an actual thing you have to design. So,
And
I think
then
that's
like
perfect.
for the just like changing the material.
Sure. Yeah.
Do you know how I would bring carbon fiber in ANSYS?
Oh, that is a tricky one because carbon fiber is not isotropic.
Yeah.
And so I think people have tried it in the past. If you have just like a rectangular block of carbon fiber.
Kind of what it is.
Okay, then you can kind of, so the way, I think we'll do the workshop probably after Thanksgiving. That's gonna probably be most likely, but I have a workshop where I show you how to do an orthotropic material. So basically you assign Young's moduli in each of the different directions. So that's probably the easiest to do. The only bad thing about that is that if you have basically your carbon fiber block has to line up with X, Y, and Z axes perfectly because you can only assign it in the X, Y, and Z axis.
Okay, so then when I do the file, I have to make it like extrude it from.
Yeah, I think what would be interesting for you actually for your final project for two of your configurations, you can do a carbon fiber where you try to approximate an isotropic material, and then do carbon fiber, but you try to do the orthotropic, and you try to see kind of the difference. It's the exact same loadings and everything. So I think that would be really interesting to see kind of the effect of that orthotropic property.
But also gonna honeycomb it when I do make it. So I don't know if that would change.
Honeycomb is hard to do because honeycombs they're so thin.
Yeah.
So maybe that could be a third configuration, honeycomb versus not honeycomb. But people in the past have struggled with meshing the honeycomb stuff. But we can talk about it maybe after. Let's talk about it after the midterm.
Okay.
But yeah, I think it sounds like.
So I know, so I just want to get your idea on it.
Yeah.
For the most part, I had the idea of analyzing stresses on a rover's gripper.
Okay.
It's so simply.
People have done that before.
Yeah, okay, so the thing is, Jerry wanted me to analyze the links on the gripper, so the links, this is essentially how the links are.
Okay.
Here,
Okay.
so yeah, it's for our linkage, so this was part of what's here.
Yeah.
So for the most part, when I analyze them, I just analyze them like half-assed, because if I were to analyze the entire assembly as a whole, I couldn't really apply any realistic boundary conditions. Just as if I were to add this, a fixed support here, it doesn't really demonstrate because this rotates.
Okay, I see.
Yeah, so I analyze the force, like, because we have it force like 89 newton, like torque force.
Yeah.
Acting on here, so I was gonna just kind of apply the force to it.
Okay.
So that could be for the most part, but I want to properly see how that force acts on all of the links, but also take into account, like, that realistic boundary condition that these rotate.
Okay. I see. Yeah, it's, I mean, so one way that you can think about it is that, you're doing basically failure tests. You're trying to see if any of this is going to fail. And so because of the way ANSYS is, you have to fix it somewhere. And so when I see a fixed support either on here or here, to me, that's looking like a situation where it kind of gets stuck, like it's kind of jammed right here. And so you can actually try both. And so you can actually, and this could be like two of your configurations for your final project. You can apply this force here, and then you can try fixing it here. And see what happens. And then you can try, so that would be the case where like this one gets stuck on something. And then you can try fixing it here and then see what happens. Same force, but you
They have one on each wall, it's just like the one.
That's kind of two
back.
extremes.
Or instead of having it all the way down there, they have it mounted right stuff there.
Just-
Which is kind of the worst.
Yeah.
Worst case scenario, it's kind of jammed and then. Yeah, I think that's a good project.
Yeah, it's for the most part. I gave them like sort of like half answer because the entire conformity, like this is one here.
Yeah.
That's gonna rotate, and this is the worm itself.
Okay.
So it is gonna close like that, like the worm here.
I see.
So I just want
Oh,
to make
okay.
sure that I want to analyze it properly because I did exactly what you did. I just put a boundary condition for fixed support inside the hole. So it stayed still and then I just applied force to it, like to the force, like to the face up here. Just because of course, of the force acting here, it's gonna act all of that, but I want to find out. I just wanted to ask if there was a way to analyze everything as a whole.
Yeah.
So that it could be somewhat more realistic.
Yeah. I mean, I probably have to look more carefully at the CAD itself. I think that'd be, I think in like 3D, so it'd be, I mean, I'd be happy to take a look too. And so if you have it today, I can probably take a look briefly after this. In my opinion. But for now, you know, I think it's not bad to have the worst case scenario. It seems like. Because those are the ones you're saying. So I think that's good to start. Maybe I'll pass it.
My senior design, like I told you, we're dealing with the lowers and there's 3 different models. My agreement thinks the best thing to do for me is either do the honeycomb or the lights.
Okay.
I think we're just doing, do a hollow light.
Okay.
So, because my job is to figure out the head loss. So every time the wave in the price curve goes by it, I got to determine how long the head, the light will last for each run.
Yeah, that sounds good.
So it's so that way I don't have to do three different models. The other 3 is flaps, which we just think it's not worth doing ANSYS. Because once it hits, it just flaps up and then goes back down. So it's not worth it.
What's up?
Project.
Yep.
And I wanna do better on the final. So I wanna like, obviously I'll take into account the points you made in the rubric.
Yeah.
Is there any way that I can get like, if my score is higher, I have to score back?
I only going to do that for like very special circumstances, like medical, like people had to miss the midterm. Normally I don't do that. But you know, the final project, I mean, we still have the midterm exam next week, of course. You're very good at taking exams for biomechanics.
I
And
mean,
so.
I'm 1 for 1. That's it. It's a small
And so,
sample.
you know, there's still like, you know, a very good chunk of the grade left. So, you know, there's still a lot of places.
A lot of places I can talk about.
No, don't think like that. You gotta think positive.
All right. Thank you, Professor.
Yeah.
Appreciate it.
Mhm.
I finished watching this God of War Ragnarok.
Oh, yeah?
That was awesome.
Oh, really?
Yes.
I heard a lot of good things about it. God of War they always do a good job with this.
Well, especially the 2 recent ones, the 2, now you can play the PC version, the 2018, the recent one. just came out. You have to wait.
Hey, Justin,
Yeah. What's up?
there you go, we got you up here.
Oh, really?
Yeah, we went drinking before this.
Okay, thanks.
If you want more, we have some more.
Okay. Well, I can't drink a drink class, but maybe after class.
Wait, why can't you drink a drink class though?
No one's trouble. The dean is like 2 floors up here.
Well, see, you only get in trouble.
Then
if
just give
people
one to
catch
the
you.
dean.
No one says a word.
In my mind, it's like, look, it's only a crime.
And I'll
to
buy
get
you all
caught.
the life.
That's how lawyering works.
You know, I can't lose this. I just booked a wedding for next year.
No one says a word, and I'll buy
Trust
you
me,
all
I
the life.
studied law for 4 years and I still,
Oh,
I didn't mind.
I
Don't worry, I got this.
I'll enjoy it after class. After class.
You didn't enjoy it on the drive home.
When I get home. I'll
If you want
tell you.
something, if you want something stronger, I got some local one.
All right, we'll see.
See, I like to think of it as when you're drinking and you're driving, you're testing your driving skills.
Well, that's a very expensive, very costly test if you fail it.
Then you just don't feel it.
Very yes.
That's impressive.
Thank you guys, I appreciate it. I'll cut that part out of the recording. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Surviving. Good. Okay. Thumbs up. All right, so it's good. It's a long weekend. So the first of two long weekends, I guess. And so we have Veterans Day tomorrow, and so we don't have instruction. Well, normally we don't have instruction on Fridays, but you guys get Friday off, which is good. And then after next week, we have Thanksgiving. And so, November is always kind of a happy time with lots of long weekends, which is good. Okay, and so today, just like I promised on Tuesday, is going to be our next ANSYS activity. So it's been a while since we've done ANSYS, or at least together. It's been a while since we've done ANSYS together in a class like this. So last time we did it was ANSYS activity 4, which I think was probably a month and a half ago. So this is the first time in a while. Okay. And so if you're curious about how many ANSYS activities we have left, we have this one. This is going to be due after the Thanksgiving break. And then I have one more after Thanksgiving. So these last two ANSYS activities, I would consider them kind of like the extra almost like extra after ANSYS. I almost said extra credit, but they're not extra credit, but they're not core to ANSYS. And so the kind of the topics that I chose for activities 5 and 6 are what I think are really cool and really fun and really useful additional features or auxiliary features in ANSYS, but not essential to the core. Okay. And so if you want to factor in activity 5 and 6 into your final project, I would say go for it. I think that's a great idea, but it's also not a requirement. Okay. And so I want to emphasize that. So activity 5 and 6, I think they're useful in a lot of ways, but also not a requirement for the final project or anything like that. Okay? But you're certainly welcome to do it. All right, so activity 5. And so what we're doing in this activity is we're going to be doing dynamics analysis, right? And so we're actually going to be simulating a moving object, which is very different and very cool. Okay? And we're going to apply it to something that's very, I think, something that maybe a lot of people have seen at some point, hopefully not have experienced it, but we're going to be simulating a car crash. Right? And so we have this CAD model here that I've uploaded onto Canvas. And the CAD model has two parts. So it has kind of a wall here, and it has a kind of a car frame, just the frame itself, just to kind of keep things simple. And what we're going to do is we're going to set this car in motion, and we're going to ram it against the wall, and we're going to see what happens. And so our objective in this study is we're going to see what the maximum speed that this car can go at and hit the wall and kind of still retain its kind of structural integrity. Okay, so that's kind of what we're aiming to do. And we can also do a mesh convergence test. The mesh convergence test is not going to be a requirement because for this one, it is going to take quite a bit of time to run the mesh convergence test because you'll see each dynamic simulation takes quite a while. And so I'm not going to make it a requirement, but this is one where doing the mesh convergence test is kind of cool, but this is not a requirement. Maybe I think I'll revise the project document online to kind of emphasize that mesh convergence test is not required. All right, and so kind of a review of kind of the new things that we're going to do in this activity relative to the old ones is we're going to use a new module. And so instead of using static structural, we're going to use explicit dynamics. And so that's going to be a first for us. Okay. We're actually going to be removing some contact conditions between some of the parts. We're going to apply an initial condition, and we're going to set up the parameters and run the dynamic simulation. Okay. All right, and so to begin, I've uploaded the activity onto Canvas. And so if you go to our Canvas site, you click on assignments, you'll go to activity 5. Okay. I have the PDF here. And so, that's important for you to download. But what's even more important is going to be the CAD model, which is this car crash analysis.igs. And then after you've downloaded that, go ahead and start up Workbench. And then we'll go ahead and start from here. Okay, so I'll give everyone a couple minutes to start up Workbench because I know it takes a while. And during that time, if you have any, does anyone have any questions?
What's IGS?
IGS, I don't know what it stands for, but it's a CAD. It's a CAD file. So it's one of the files that you can export SolidWorks assemblies out of. So you can export IGS as well.
I like the name of that.
I thought very hard about it. All right, so does everyone have ANSYS Workbench open? Okay. All right, so let's go and get started. And so first thing we're going to do is we're going to start just like we did before. So before we drag static structural out there, but this time we're going to drag explicit dynamics. Okay, so go to the toolbox on the left-hand side, find explicit dynamics, and go ahead and drag that over. And then you should open up kind of a module that looks like this. Okay? So first thing we're going to do is we're going to add our geometry. And so we're going to right click on geometry here. We're going to click on import. We're going to browse and we're going to go to the file that you just downloaded from Canvas, which is carcrashanalysis.igs. Okay? And it should import without any issue because it's, I've done this 5 times now. And so it should work. All right, one other thing that we're going to do before we jump into ANSYS Mechanical is we're going to add some material properties. And so we're going to double click on engineering data. Okay. And so when you double click on engineering data, you'll see that we have structural steel here. Okay. And so good old structural steel. So our usual one. And so before what we've done when we've added a material, we've kind of, I would consider added from scratch. But ANSYS actually has a material library here that, I haven't told you about before because, when I was doing this class for the first time, I actually didn't know about it either until then. And so if you click on this button right here called Engineering Data Sources, and so there's kind of a book next to it. Okay. And so after you click on Engineering Data Sources, it's going to open up this new window here. Okay. And then what you'll see is that if you kind of look on this kind of upper window right here, these are all the lists of engineering data sources that are in ANSYS. Okay? And so what we have here are ANSYS granted materials, general materials, additive manufacturing, geomechanical, composites, and a lot of stuff. Okay? So we're going to go under general materials. And so we're going to click on that. And then after you click on general materials, actually, let me go ahead and circle that. And so after you click on general materials, this kind of window in the middle here is going to change here, right? And so under general materials, you'll have all these different metal alloys that you can choose from. And so for our analysis here, we're going to click on aluminum alloy. And so we're going to add that to our analysis. And so go ahead and click on the plus sign next to aluminum alloy. Okay. Right. And so after you click on the plus sign for aluminum alloy, you should see a book appear next to it. And so what that book tells you is that you've added that aluminum alloy to your project. Okay. And so that's the main one we're going to use for the project. But just for fun, we're going to see what happens when we have a car made of plastic. So if you kind of scroll down the list of general materials, you'll see that there's an entry here for polyethylene. And so we're going to add that to our project as well. Okay, so we're going to click on the plus arrow next to polyethylene to make sure that we have this book next to it. Okay? And so in total, you should have 3 materials in your project. So you should have structural steel, you should have aluminum alloy, and you should have polyethylene. And so if you want to confirm which 3 materials that you have, you can click on this button again right here called Engineering Data Sources. And so that's going to remove this menu. And so if you click on that again, you should see you have 3 materials here. So aluminum alloy, polyethylene, and structural steel. Yeah.
Is the polyethylene supposed to be under the general?
It's under general materials too. So if you click on general materials, it should be down there. You might have to scroll down for it. Are you? Is it? It might be a version thing. All right. So if you maybe they might have moved it in the 2022 version because the one I have here is 2021. So
No, not for me.
oh, you have it? Okay. If you're not seeing it, you might click on general nonlinear materials. It might be here. Nice. If you don't have it, then don't worry about it for now. It's kind of just an extra thing for the end, and then we can look at it again later on. Okay. All right. So was everyone able to at least add aluminum alloy to their material properties? Okay. All right. And so if you've gone ahead and added that, let's go ahead and close our engineering data here. And then we'll double click on model here to enter into ANSYS mechanical. Okay, so go ahead and double click that. And we'll wait for a couple minutes to for ANSYS mechanical to start up.
You double click model?
Yeah, just double click model.
It's like a Ford, almost 90s Ford.
It might have been.
In a century.
Yeah. Very, very blocky. I don't know if that was, so I got this CAD model from another author online. And so I think, I don't know if he was going for a specific car model. I think he just made a bunch of blocks and just added a bunch of fillets to it, so. I don't know. He may have been. It's been a while since I've seen his video. All right, was everyone able to open a mechanical? Okay. All right, so let's go ahead and go through our process now. So let's go ahead and first let's assign our materials. And so if you click on the plus arrow next to geometry, you'll see that we have two parts here. And so one part is the car, and so part one is the car, and part two is the wall that it's hitting against. Okay? We don't really care about the wall, and so the wall is just kind of there just to for us to hit something into. But what we do care about is the structural response of the car. And so you're going to click on part one here. Okay, and so make sure the car is visually highlighted in the image here. And then after clicking that, you're going to go down to material in the bottom left. And then you're going to click on the assignment. Instead of structural steel, you're going to click on aluminum alloy. Okay. All right, and so once you do that, you've set the material property of the car to be aluminum, and we're ready to move. We're ready to move on. Okay. Next thing we're going to do is we're going to remove the connection between these two parts. Okay. And so remember, whenever you have an assembly of parts, ANSYS you have to define to ANSYS how those parts are going to connect. Right? And so if you remember from activity 4 when we did our bridge, we spent quite a bit of time to make sure that all the parts were kind of perfectly bonded to each other so that they all deformed together. Okay. And so for this case, we actually don't want these parts to be bonded together because we want the car to hit off the wall and then it's going to kind of bounce off afterwards, right? And so for this case, because it's been made as one single assembly, and you'll see here that the car has already kind of made contact with the wall. There was kind of a contact region that was created. Okay, and so if you click on the plus arrow next to connections, and then you click on the plus arrow next to contacts, you'll see that there is a contact region here that is defined between the car and the wall. Okay. And if you scroll down here in the bottom left, you'll see that this connection is bonded. Okay? And so what this means is that these two parts are going to be kind of moving together as if they were kind of welded together. Right? And so we want to remove this. And so we want to make sure that the car is not going to be stuck to the wall after it contacts it. And so all we have to do here is we just have to delete this. And so we're going to right click on the contact region here. We're going to click on delete. And so by deleting it, the car is kind of free to kind of hit the wall and kind of bounce off and kind of be its own entity. Okay. So that part's really important. So you want to make sure that you delete that contact region so that the car is free to kind of bounce off the wall, just like that. Okay. All right. Any questions on any of this so far? Right. Okay, so next part is meshing. And so let's go ahead and put a mesh on this guy. All right, and so we're going to create I'm going to create 4 meshing settings here. So I'm going to create a method object for the wall. Okay. We'll call this wall method. Okay. I'm going to create a sizing setting for the wall. Okay, so this is wall sizing. And I'm going to create the same things for the car. Okay, so I'm going to create a car method. And then also a car sizing. Okay.
2 methods to sizing.
Exactly. Yeah. Mhm. Okay. So let's do the methods first. And so the only thing that we really have control over here, because the car actually is pretty thin. And so actually, if you were interested, you could actually redo this analysis by changing the car into a shell. But we're not gonna worry about that in this case. But it's not quite a shell, so there is actually some thickness in there. But if you move it to space claim, you can kind of do a mid surface and get a shell out of this. And so that's one thing you can consider. But for now, we're going to assume that it's 3D. And so for the method, the only thing that we are going to be able to do is select the element order. Okay. So normally, when we do static analysis, we do quadratic order, right? And so we've basically just been doing quadratic order all throughout. But for dynamics analysis, because it's so computationally intensive, it's a lot more resource intensive than statics. We're going to be limited to linear here. And so you want to make sure that for the wall and for the car, the element order that you select is going to be linear. Okay. Okay. And so, the only reason why we made a method setting for the wall and for the car is to make sure that we can set a linear element order. Okay. Otherwise you're going to be waiting for hours for your simulation. Our question, so is it because we're limited by our software since our computers likely can't handle it? That's basically it. Yeah. It's not so much the software license this time, it's your actual computer itself. So even if you have like a very powerful gaming rig, it's still going to be pretty intensive if you do quadratic elements. You're certainly welcome to try it, and so maybe after the class you can try it with quadratic, but for this first run, just to make sure that everyone can get results, I want everyone to run it with the linear element. Okay. All right, next is the sizing, and so let me go ahead and change the units here. Let me change it to SI. Oh, it is an SI. Okay. Let me change it to centimeters actually. Okay. And so for the sizing, for the sizing, we want all of our attention to be on the car, and so we actually don't really care what's happening to the wall itself. And so we can actually make the mesh on the wall a lot more coarse. And so I'm going to set the mesh size for the wall to be, let's say 8 centimeters. Okay. And then for the car, I'm going to go a lot smaller than that. So for the car, let's say I'm going to do 1 centimeter on this. And let's go ahead and run our mesh here and see what it looks like.
About the mesh itself.
What do you mean the mesh itself?
If you click on the mesh.
Oh yeah. I mean, we want to set kind of independent sizes on the car and the wall. Okay. So I set the wall to 8 centimeters. So you can see it ends up being very, very blocky, but we don't really care what happens to the wall.
And then the car
was 1 centimeter. I actually might reduce this a bit more. So let me try 0.8 centimeters. See what that looks like. So 0.8 looks a bit better. So, we're not going to be able to get a very fine mesh on this because again, we're going to be severely limited by the cost, but try to get something that kind of looks somewhat similar to this. Okay. And if you want to grab a screenshot here, if you kind of read the problem document, one of the requirements for this part is to grab a screenshot of your final mesh. Okay. If you want to grab a screenshot of this and kind of stash it away, then you don't have to worry about it. And so if you were interested, so remember the mesh convergence test is optional, but if you were interested in the mesh convergence test, you would change the mesh of the car and then kind of go from there. Okay, but again, it is optional. Okay, so next step is going to be the boundary conditions. And so we're going to start with the fixed support. Okay. And so to add a fixed support, we're going to right click on explicit dynamics A5, and we're going to add a fixed support here. Okay. And so we want to make sure that the wall is going to stay still once we kind of ram this car. Okay. And so we're going to add our fixed support. And we're actually not going to set the front of the wall to be fixed. And so we're actually going to set all the sides of the wall to be fixed. Okay. And so your fixed support should look something like this. And so you should have basically 4 sides of the wall that are fixed just like that. Okay. So this is to kind of simulate the fact that, this car, it's not going to be hitting just this kind of small wall like this. It's actually going to be part of a much bigger wall. And so the wall is going to be fixed by the fact that there's a lot more wall around it.
Should it be 6 faces or?
Just 4. And so we just want the four skinny surfaces.
Oh, whoops.
Yeah. And so you don't want to fix the front of the wall, and you don't want to fix the back of the wall.
How about under? Oh,
Underneath as well. Yeah. So the front of the wall especially. So we basically we want a little bit of kind of flexibility on the front of the wall, because when the car bumps into it, the wall itself is going to kind of indent. And so we want to make sure that we kind of capture that elastic response. And so if we completely fix that wall, then it's going to lead to some weird stuff in the simulation.
That's one really tough wall.
Yeah. I mean, the wall is made of steel, and so it's going to be very tough anyway, but we want it to have a little bit of give so that, it's a little bit more realistic. Okay, and so the other boundary condition that we're going to specify here is a displacement condition, okay? Because we want to make sure that this car kind of stays on the road, okay? So we want to basically constrain it in the Y direction. So we don't want it to kind of hop up or go down because the car is going to stay on the road the whole time. So we're going to right click on explicit dynamics. We're going to set a displacement condition, okay? And so go ahead and click on displacement. And we're going to apply it on each of the undersides of this shell. And so you might have to zoom in here. And so we basically want to constrain all the undersides of this car. Okay, so you're going to have to hold control and click. You might have to zoom around with your mouse. Okay. And so you should have 8 faces underneath. Okay. And then we're going to set the Y component of this to be 0. Okay. And so in the end, you should have two constraints. And so you should have a fixed support on all 4 outer edges of all 4 outer faces of the wall. And you should have a displacement constraint on the bottom side of the car itself. Okay. Just the Y component, correct. Yeah. Because we're gonna apply velocity in the X direction, and the Z direction kind of comes out of the page, and so we don't have to worry about that. Okay. Question? So the Y direction, we put it to be 0, and so you're going to click on displacement here, and then this Y component of the displacement you're going to set to 0, just like that. Any other questions on this step? Yeah. Right. So we're basically making sure that the car stays on the road. So we're basically, if you look at the Y direction here, the Y direction is going up and down. And so by constraining in the Y direction, we make sure the car doesn't clip into the road or kind of go flying off like that. Yeah. Yeah.
And what scenario would be fixed back?
Exactly. Yeah. I think for this one, you could probably fix the back of the wall and it'll be okay. We just don't want to fix the front of the wall. So that's the actual contact surface. The wall is going to be pretty rigid, and so it's not going to, the backside is not going to move all that much. Okay. Any other questions on the constraints here? Great. All right, so believe it or not, we're almost there. And so we just have two more things that we need to set. And so we need to set the initial conditions and we need to set the end time. Okay, so let's start with the end time here. And so remember what we talked about on Tuesday. When you run a dynamic simulation, you have to kind of set two things. And so you have to set the time step size. And so that's how much time is going to be in between the frames of your video. And you have to set how long the simulation itself is going to go for. Okay. And so for a car crash, the car crash is going to happen very, very quickly. And so, we don't have to actually simulate all that much time because the car is going to impact it. And then, it's all going to be over kind of in an instant. And so we don't want to set the end time here to be anything too large. Otherwise, our simulation is going to go on for a very, very long time. Okay. And so for the end time, we're actually going to set something very, very small here. And so we're going to set 0.00075 seconds. Okay. 3 zeros. 75. Yeah. Okay. And so the two settings that the two places you have to click here is you're going to click on analysis settings. And so after you click on analysis settings, then the bottom left of the screen is going to change. And then what you'll see in the bottom left there is that there's a row for end time that's going to be highlighted yellow. And you're going to set that to be equal to 0.00075. So 3 zeros. All right, so that's the end time. So was everyone able to set that one? That one you actually need to specify. It's not gonna let you run a simulation besides that. And so if you the other setting that we would normally have to set here is a time step size. But when you're running explicit dynamics, ANSYS actually sets that for you. So the only thing you have to specify here is the end time, and then ANSYS will determine what an appropriate time step size is going to be. Okay, so we don't actually have to worry about the time step size, okay, which is nice. All right. Fixed support. Oh, so for the fixed support, it's going to be everything around the wall, just like this. So we want to make sure that the wall is not going to move. It's not going to translate after the car hits it. So we're going to fix all the sides, but don't set the front of the wall here to be fixed because we want there to be a little bit of flexibility on that. Yeah. All right. And so the last thing we're going to set here is the initial conditions. And so, we want to basically make sure that the car is going to hit. And so we're going to give the car initial velocity. So we're going to right click on initial conditions. You're going to click insert, and then you're going to go to velocity here. Okay. And so what this is going to do is that it's going to apply a velocity to whatever object that we choose. And then that's how the simulation is going to start. Okay. So we're going to click on velocity here. We're going to make sure that you're on volume selecting mode or body selecting. And so you're going to click on the car. And so that's going to be your body there. Okay, so you want to make sure you select the entire car when you're applying this velocity. And then we're going to change it so that we can apply it in terms of components. And then we're going to set an initial velocity of I think in the document I gave you basically the speed of a speeding bullet, but let's start a bit lighter. So let's start at 100 centimeters per second. Negative, yeah, because you want to make sure the car is going to contact the wall. Because if you look, the positive X direction is going to the right, and we want to make sure the car actually hits the wall, so it's going to the left. And so you make sure that your car here has an initial velocity. I'm choosing 100 centimeters per second, but you don't have to do that. You can set speed whatever you want. And we're just about ready to run the simulation. So let's make sure that we get some results here. So let's, just like we've done before, let's right click solution A6. Let's look at the total deformation. Let's look at the equivalent strain. So equivalent elastic strain, and let's look at the equivalent stress as well. Okay. All right, and so with all of that set, make sure that you have your velocity initial condition, make sure that you have your end time. You have your two boundary conditions, which is the fixed support and the displacement. And now you can just go ahead and click solve. And you're going to be waiting here for a few minutes because this is going to take a while. So while this is running, I'll go ahead and make my rounds. And so if you're have any questions on the settings, I'll go ahead and help you at this point. But once that's done, we'll kind of look at the results together. And if you need help, just go ahead and raise your hand, and I'll come back to you.
It's speeding up now.
Hands turned on.
I got error already, so.
What did it say?
I'm gonna, it says I can't find the file, so I'm just gonna reopen it again.
Okay.
Find it. That's what it is.
Okay. So that actually finished a lot sooner than I thought. So I guess these new computers are pretty good. I remember when I did this activity last year, like I was waiting here for like 10 minutes. Maybe it's because that was my laptop. All right, and so I'm gonna go ahead and play the animation here so you can kind of see what's happening. And so there's a button down here for play. And so actually, this actually not much is going on here because the speed that we picked was so slow. So actually, let me go ahead and increase this just so that we can kind of see what's going on. So let me do 150 meters per second. So 150 meters per second. So we're going to super fast. I remember now. So I remember I changed it to 150 before just so that you can, so it's kind of a little more dramatic once it's 150 compared to. Yeah, so if you're not seeing that, if you're not really seeing any results with 100 centimeters per second, you can go ahead and change it to like 150 meters per second. And that's the one I have in the document. So I think the results are going to be a little bit more spectacular for this one.
I'm getting errors, sir. It's getting a mesh error. Oh, it doesn't like that sizing. Let's see what this looks like.
There we go. All right. And so if you have a much higher speed, you should get kind of results like this. And so, yeah, the car is going to bounce off, and then you can actually see it actually starts to vibrate. And so remember what we talked about on Tuesday, whenever you have any kind of dynamic situation, there's always going to be some degree of vibrations. And so kind of all that wiggle, kind of all that like jello stuff that you're seeing is the vibrations of the car. And so of course, this car isn't physically braking. And so, the material model that we chose for this was strictly linear. And so you're actually not going to see the car just completely splatter against the wall. And so it is going to kind of bounce back. So that part is a little bit unrealistic. But I think if you shoot a car at a wall at the speed of a bullet, it's probably not going to survive that. But but this is kind of an example of what you can see with explicit dynamics. All right, and so if you're able to get this, that's great. If you're having trouble getting this result, go ahead and raise your hand, and I'll kind of make my round. I'll start making my rounds now.
I'm getting all sorts of message. Oh, that's mesh. I ignore the file. It's just going to say that all the time. That was set to 0 in that match that I set it. If we can't do it afterwards.
Let's just set this to be.
This should not change the mesh, but it should get rid of some of those.
Keep increasing.
Oh my gosh.
What do you do?
I just try to change the sign.
You need to. No, it's like, it's graphics.
Okay.
It's just weird.
Try to go a bit smaller. Change this back to.
So that's just basically all it is. I just have to play around until it's satisfied.
You might try to recreate the project and download the file again from scratch. It could be the file got corrupted somehow when you download it. So I would try downloading the geometry again.
Oh, yeah.
See and kind of redoing stuff. Start with just the mesh and see if you can get that.
Yeah, I'll try.
Okay. Is this with 100 centimeters per second? Or
Yeah.
Not the initial. Or click the plus arrow next to it. Yeah, so you're not going to get any bounce off of the 100. So let's change it to 150 meters per second. Go to units. It is pretty extreme, or minus 1. So for the mesh, I think that's just one thing. So your mesh looks fine. So
Why would it not show?
I think there's a setting up here. So like when you're viewing the results, there's like the view thing right there, and then you can check to see either view the mesh or not. So, but it's just yeah. So it's running the simulation.
Yeah.
So it's probably not. Probably under like solar.
Why didn't you show that?
Yeah. Show. Oh, so the rest of it, so the next immediate part is I want you to find the maximum speed. And so the max, and so if you look, one of the results, the stress. So the maximum stress that the car can handle before braking is 55 degrees. You just gotta change the speed exactly. We'll see, it's gonna be way lower than this because the speed of the speed limit. So you're gonna basically lower the speed until you find.
Oh.
I mean, yeah, that's fine too. I mean, your car's not gonna. Your car's gonna. So maybe right here. Well, this is a 9% here, so let's change the units. Let's put it on. That's the first one. So now it's in Pascal. So now it's I mean, yeah, like that. So yeah, I mean, we can change like a this is actually not always so weird. People get like stress values on low because mostly because of stress. So the entire thing. Very nice. Still running. Yeah, so let's just. Yeah, so this is a pretty. You're not gonna see that. Increase the speed level. So right now it's -1.
Don't be so angry. Gosh.
This is pretty extreme. And you have to really identify. But when you increase the speed, Yeah. So right now.
That's more often, I'm still meeting with my senior design. Use the class time, which is grind out.
Just off the notes of the.
The rest. I just want to say. Yeah, heat injection. Basically, whatever I got. One thing that's good question.
You said basically be able to do the 100. You gotta do next week. You have to do so. Holy shit. No. Nah, my doing one job. I wrote 476 hour she basically does it. It's like coding for you. She basically knocks it out all out for you, bro. Like you can chill class and you have a free time out, you ask her a question, she'll basically. You have all the coding and you just basically just type out the report.
If you're because then a couple other people having issues.
I guess I solved it today, but I was missing like and they bullshit with them before.
Just closing all of these work.
Then, like, I'm going into this semester, I got to notice like, oh.
Okay, let's try creating a refresher.
Oh, it's weird. Yeah, so then I went to the office financial aid and I. Yeah. I did it last year. I did it last year, that's not, well, all I really needed to was into being a group.
Yeah, maybe
It's just one.
looks like it seems like.
And then I have, over
This
6
laptop just is always had really weird issues. They're
Try.
There's an end user. There's not that many. Not yet. Yeah, I know.
Okay.
Yeah, that's what I was like, I didn't.
But by default, it actually should be. So maybe, let's try not messing.
The one
with this.
before, it sucks, and I know he has one before.
So let's just make it.
Yeah, he has one.
Go ahead and finish. Try to-
Like, unless I was like, Zoom.
Nice. Yeah, that's good.
One more question I started to ask is, so you have ANSYS like the full license, right?
Not on this computer, on my lab computer.
Would it be possible, like I've been trying to run the info?
Yeah.
Would it be possible at some point for me to ask you to run a full for CFD?
Oh, yeah, I can let you into the lab and. Yeah, just, so my student is actually using it, so we actually. Not supposed to, but he coming here after work. So she's into it too, so, so once he's, I think he'll be done. Yeah,
You wanted this, right?
yeah. Actually, yeah, there's actually one more. So yeah, you can actually see the kinetic. Should have done this. So, let me try for a second. Yeah. This is actually. You can actually see how the split is between kinetic energy. Because when you first start the simulation, the car is going. Then as it contacts it, all that kinetic energy gets. But then because we're looking at a perfectly elastic situation, then it actually bounces back.
In cases where realize you wouldn't mention this for the last.
Because we're looking at a perfectly elastic case, it's going to bounce back. It's going to real life would stop. Yeah. That's fine. I want to see both the fixed ports. If you click on this one shows both. And so I wanted to see what. Sorry, Zoom people, how are you guys doing? Yeah, so if you if you want to see it kind of bounce off like this, you're going to have to increase the velocity. So the velocity I'm using here is 150 meters per second. And so if you really want to see it kind of bounce back, it's a little bit unrealistic because it's not actually going to bounce back like that. But That's how you do it. Okay, so there's a couple more things I want to talk about with you guys before you guys head out. So first thing is in the results, I asked you guys to show something called the energy summary. And so I just showed kind of someone else about this. And so if you click on, after your simulation's done and you play the animation to make sure that it's good. One thing that you can actually show is you can see the breakdown of kinetic and internal energy in your system. Okay? And so if you click on solution information here, and so instead of solver output, you're going to change this to energy summary. And so what this is going to do is that it shows you kind of the summary of how the different forms of energy are in your simulation. Okay, and so if you click on energy summary, you should see a graph that looks like this. Okay? And so it looks kind of interesting here, but let me kind of explain the different trends. All right, so at the beginning of your simulation, all of your energy here is kinetic because we've given the car an initial velocity and the car is going to go hurtling towards the wall at its velocity, right? And so that's why at the beginning of your simulation right here, this blue curve is kind of at a maximum, right? As the simulation goes on, that kinetic energy starts to go down because what's happening is that the car has contacted the wall and it's starting to kind of crumple up, okay? And so as the kinetic energy goes down, the internal energy is going up, okay? And the reason the internal energy is going up is because, all that kinetic energy that the car had is now going towards, kind of crumpling the car up because, it's deforming the car, okay? And so both curves kind of reach an apex kind of at this point right here, okay? And so at this point right here, the kinetic energy is at its lowest and the internal energy is at its highest. And so at this point, basically the car has kind of reached its maximum scrunchiness and it's almost stopped moving. And so normally, if this were in real life and this car were hitting the wall, the simulation or the situation would stop right here because the car would hit the wall, it would crumple up, and then that would be it. Okay. But because we've assumed that the car is perfectly elastic, what happens after that is the car actually starts to spring back. And so, it starts to kind of uncrumple because it's kind of pushing back against the wall. And so that's kind of this pushback that you see right here, and it kind of wiggles from there. Okay? And so this energy summary here is pretty interesting because you can kind of see the point where normally the car crash would stop, but then afterwards you can kind of see that the energy start to vibrate a little bit. So this is kind of the vibrations that we talked about on Tuesday. That's characteristic of dynamic simulations. Okay? All right, so that's one thing. Another thing that you'll notice is that if you view the total deformation plot, it's actually a little bit misleading because if you look at the total deformation, it makes you think that if you kind of stop it right at the beginning, it makes it look like the entire car has this real large deformation. Okay? And so deformation is actually pretty misleading in dynamic situations because the way that deformation is measured is that it takes the difference between where that mesh point started or where that element started versus where it ended up, okay? And so when you have a dynamic situation, you might have a lot of motion because things are moving quite a bit, okay? And so even though it may seem like this car is experiencing lots of deformation, the only reason is because the car has bounced off and has come back, okay? What we actually want to see here is the strain, because the strain is going to show us, how much the car itself is kind of deforming in shape. And so, I had you guys kind of show the deformation and the strain here to kind of illustrate that point where, for a dynamic situation, most of the time you're not going to be looking at deformation. You're going to be looking at strain and you're going to be looking at stress. Okay. And so that's kind of the number that you should kind of see. Okay. And so from here, the rest of the activity is, fairly straightforward. So let me go bring up the PDF again. And so from here, we've done pretty much everything through problem 4. And so we've run the simulation, we've looked at the results. Okay. The next part, problem 5, I want you to find the maximum velocity that you can ram this car into the wall at. Okay. And so if you assume a maximum yield strength of 55 megapascal, I basically want you to modify the speed of the car until you get a maximum strength of 55 megapascal. Okay. And so we come back to the simulation here. We come back to ANSYS. You can see now with a speed of 150 meters per second, you can see that I'm getting an equivalent stress of about 2.17 gigapascal. Okay, and so that's obviously way too high, which makes a lot of sense, right? If you fire a car at a wall at the speed of a bullet, you know, it's probably not going to survive that. Okay? It isn't megapascal, but it's 2.1 times 10 to the 9th, which is gigapascal. Okay. And so you want to be something closer to like 5.5 times 10 to the 7 Pascal. Okay. And so to get this, you know, what you're going to need to do is you're going to need to modify the speed, and so you're going to lower it, and you're going to lower it pretty significantly until you reach a maximum stress that's less than 55 megapascal. Okay, and so that's how you do problem 5. Problem 6, I basically want you to repeat problem 5, but instead of using aluminum alloy for the material, I want you to change it to polyethylene. Okay, and so you know we can have a little fun experiment to see what happens if you have a plastic car. And then problem 7 is just just the usual. So you're just going to summarize your findings. Okay. All right, and so that's about it. And so it's I think the simulations themselves can take a while, but there's really not much more we can really do with dynamics. And so we have about 20 minutes left in class, and so I'll make my rounds again. And so if you're still having issues, I know a couple of people are having issues with the mesh, and so I want to make sure I get those sorted out before the end of the day. And then we'll wrap it up. But that's kind of it for the activity. And so if you have questions on Zoom, go ahead and leave a comment, and then I'll kind of make my way back in maybe about 15 minutes.
What is it? What kind of baseline is it?
Yeah, so for the wall, it doesn't really matter what material we're using for it because we're not measuring any kind of stress or strain. And so we just need to be kind of a rigid rock, basically.
So we are measuring stress and strain, like of the car of the.
Exactly, right. And so if we were worried about the wall deformation itself, the stress in the wall, then we would change the material of the wall to match whatever.
Like the steel wall.
Right. So for this case, actually, it'd be interesting. Actually, if you change the wall to material of plastic, you might actually see the wall kind of indent and lock. And so right now, you're not really seeing the wall react because it's so rigid. But if you change the wall to plastic, you actually might see the wall kind of punch in. So I think that might be fun to do. Yeah.
I'm trying to see after the partner just disappeared. Oh, I don't know if it's simulation thing or accident or something.
So we're having this issue too. Mesh. I think it was
Because the mesh showed up. Okay, so it's just. Oh. Oh, that's why.
That's what I got.
I don't know how that happened. At all. Okay.
It might have been because you can control on the mouse still sometimes.
And as far as like the mesh goes, the mesh is fine.
Yeah.
So what?
That can happen with dynamics. It's a
Oh, it's everything.
yeah. For me. Okay. Okay. Yeah, let me help you with it.
And precious.
After you started, you crashed on. For the mesh, prioritize higher quality at the cost. You sent me a screenshot. You got me a video, so. Okay, yeah, just email me a screenshot. You got it. I was able to get past that error.
No,
Okay, yeah, send me a screenshot. Let me see if it's the same one that you screened.
because when I send it to here, it works. But then when I try to change it, then it doesn't work anymore.
Okay.
And somebody's saying the problem is in the solver. It's not here, like they saying that if the only thing is the solution, then there's something wrong with the solution then.
I see. So let's see the mesh.
It's either that or it has to do with the additions. It's possible that different addition.
This is 2022.
Yeah. Oh, whoops, I didn't say anything. Well, even not for me.
I think it does linear by default.
Oh, that's because,
Oh,
well,
I
that's,
think you might have a different issue with someone back there. Something with the solution.
oh, that's because it's not. That's why.
So when you solve it, I should have read the error about it.
Well, I'm just reading because other people is having that same problem. Yeah, there we go. Same thing. And I did clear it. It just gives me the same result.
Same thing.
Yeah.
I wonder if it's an issue with your file path. And so it might be because usually ANSYS doesn't like spaces in the file path. And so you may try to move the project, you might try to run the project from a folder, like maybe on your desktop that doesn't have any spaces in the file path. So you can try that and see if that works.
I'll try to make it as front as possible. And that doesn't work, then maybe it's an addition issue.
Mm. Yeah, you can try it and see.
Yeah, you know what? If it is an addition issue, that's gonna be.
That's okay. But yeah, keep me updated.
Yeah.
Try the file path because it's not the first time I've seen that error.
Yeah.
And I'm pretty sure I fixed it in the past by changing the file path.
Hmm.
Just move, or just open up a new project from another location, like your documents.
Actually, let me see. Yeah, I'm gonna. Yeah, there was a lot of path. I did that because it's organized.
Yeah, because it might be because of the finite element method on your spaces in here too. So yeah, try moving into an upper folder and see.
So I got.
How you guys doing? Okay. Okay. Okay.
That's sort of what it's after.
Yeah.
So for this class, that's a combination of different relationships.
Yeah.
Yeah, so the yeah. So we add just add.
Yep.
So then I got that. Yeah, so it's 2 and 3 make it 0.
Exactly.
Oh, yeah.
Exactly. Yeah.
And then how solve with this.
So what you're going to do, so you have this kind of 4x4 matrix, and you have this 4x1. And so you're going to input that in that. So, sure. You're just going to define the matrices, and so you're going to make a 4x4 matrix, and you're gonna set the entries equal to this one basically. And so you're basically going to make this 4x4 in MATLAB. You're going to make this 4x1 vector in MATLAB, and then you're going to do matrix backslash to the vector, and then that's going to give you your answer for that.
Yes, I can get deformation.
It's going to give deformation.
And that's the D word.
Right. So backslash is basically the same thing as matrix inversion. So basically, to get the deformation, you invert this matrix and multiply that by the same. But backslash is kind of like a shortcut to do it. And then to get the reaction forces, you're going to take your deformation result, and so whatever you get the result for deformation, and then you're going to multiply this matrix by this one, and that's going to give you F1, F2.
Whatever, so we get something to do with proof of.
Exactly. Exactly.
So we take this
You could then you could find fun. Yeah, so it's backslash. So this was forward slash right here. Oh, backslash is actually this one. So I like to use the symbol A, and so like A would be like your stiffness matrix, and then you backslash, and then for the forcing vector, you can include like F. So A is your 4x4, B is your 4x1, and that gives you your results. Yeah, 441.
Not sure how to start this part.
Able to get 1 and 2.
Yeah, I'm not sure how to start that.
Right. So 3 is going to be basically you're going to manipulate these two so that you get TCS up top and PCS on the bottom. Remember, these are transformation matrices. So when you multiply two transformation matrices and their inner dimensions agree, then they're going to cancel out. Because if you look at the answer of part 1, you have MAB R TCS, and for part 2, you have MAB R ACS. And so they both have MAB. And so you want to multiply them in a way that the MAB is going to cancel out. The problem is MAB shows up on the left. Exactly. And so for this one, you want TCS to appear in the top. And so you would actually take the inverse of this one. So TCS appears at the top, MAB on the bottom, and you do inverse of this one. The labs cancel out.
So it's just multiply that.
Exactly.
Okay, so I was trying to do it like the way you should in class, but like they had equations too.
Yeah, you're just matching the same.
Just compared to T7.
So this is 2D. So the 2D one is actually going to be just sine and cosine. Yeah, it's oh. Yeah, but for the last one, you're gonna have to do some operating too, because basically what you want basically a transformation matrix of the two ACSs. So you have ACS upper or ACS lower, because everything you did here was for the lower body. So this is ACS for the lower body, and what I've given you in part 4 here is the two transformation matrices for the upper arm, excuse me. So lower arm, upper. So the transformation matrix that you want is ACS up top of the lower arm, and then ACS on the bottom of the upper arm. And so you're gonna have to do a little bit more like matrix multiplication of these two, and eliminate some of the inner ones. So again, I'll give you a hint. So you're gonna use the pinch of part 2 together with two given matrices in part 4, so that you can get one transformation matrix for the two ACSs. Because this. And so this ACS right here, this is for the lower. And this ACS that I do here, this one's for the upper. And so you want this one. This one should be in the bottom spot, and the one up here behind the right to left. You can do this as long with this. Let's find to get ACS this one in the top.
Okay, so the final floor.
So they're both ACSs. And so one's going to be ACS for the lower arm and one ACS for the lower arm. It doesn't matter. It's you can do either one, and they're both going to be this. Yes. All right, so that's it for 410. So sorry guys, I cut up a little bit, but thank you guys. It was a long weekend, so enjoy yourself. Remember our midterm is next week, so and we have a good weekend. See you next week. All right, Zoom people, sorry about that. Got kind of caught up a little bit. Oh, okay. All right, you were kind of talking. Yeah, Ryan, some people were having that same issue. Yeah, there's some issues with the meshing. I'm gonna upload the CAD file again. I think that might be an issue. And so I'll go ahead and do that right now, and then you can check with the new CAD file. As for how close you need to be to 55, not that close, maybe within like, you know, if it's like as low as 40 or as high as like 75, that's fine. Yeah. Okay. All right, thanks guys. Have a good weekend. I'll see you next week.